All right, this lesson is coming from Chapter 7, Section 3 in your Calculus 30 Red Stewart textbook. For the Calculus 30 course, we're talking about derivatives of other trigonometric functions here today. We just got finished talking about derivatives of sine and cos. So d over dx of sine of x, oops, it's a nice x, eh? Like that. Of sine of x, I was going to do theta, but then I realized I did x here. So is what? Cos of x. Awesome. And we graphed that. We graphed the sine, we took the derivative, we graphed the derivative. Now that's way back here. Let's see. That's right here. Okay. Yep, right there. Sine. We take the derivative, we graph it, ends up to be a cos. Wonderful. We know that already. Good. We also know that d over dx of cos of x, in the same fashion we determined, was negative sine of x. So the derivatives of sine and cos are actually related there. Those ones we know. Now what about the derivative of tan of x? Right? What's that? Well, we could figure that out. We could figure it out actually mathematically. You know what? We know that there are some trig identities that relate tan with sine and cos. So we know that tan of x actually equals what? Who remembers? Sine x over cos x. If you said that, you are absolutely correct. Sine over cos. So if we now took the derivative, d over dx of tan x, then we have to take the derivative of this right here, right? And we could do that using the quotient rule. So the derivative of sine x over cos x is this. Derivative of the top, cos x, times the bottom, cos x, minus the top times the derivative of the bottom. Follow me so far? Divided by the bottom squared. That's cos squared x. So that's our first step. We do the chain rule for, again, just once again, for the equivalent of tan. Tan is actually equal to sine over cos. So if I want to find out what the derivative of tan is, I could just find out the derivative of sine divided by cos. So now on to simplification here. And we have cos squared x plus sine squared x all over cos squared x. Okay? If you get to this point, can we simplify this any further? So is there something that you recognize here from pre-calculus 30 that you would be able to simplify? Well, if you said cos x plus sine x, cos squared x plus sine squared x equals 1, you would be absolutely correct. And that's something that we're going to do. So that's 1 over cos squared x. And how can we write this a different way instead of as a fraction here? What's 1 over cos squared x? You got it. Secant squared x. So, by way of derivation here, how do we find out what the derivative of tan is? Well, we could express it in terms of sine and cos because we know each of those derivatives. And we could do the quotient rule and come up with secant squared. So, secant squared is actually the derivative of tan with respect to x. Okay, so there's our other derivative, one of the other derivatives. So now we know sine, we know cos, and we know tan. Similarly, all right, let's do one more. We'll do one more proof here. And we'll do this one in blue. Let's say that we want to find the derivative of, one other one we could do is derivative of cosecant. Okay, let's do derivative of cosecant x. Now, hopefully you remember your reciprocal identities. Sine x is 1 over cosecant x. Cos x is 1 over secant x. And tan x is 1 over cotan x. So the reciprocal identities here, sine with cosecant, cosine with secant, and tan with cotan. Sorry if I went too fast there. But if you remember from previous classes, if you've been in my class, I always help you remember this by saying we have a co and a no-co. We have a co and a no-co. We have a co and a no-co. So co's and no-co's always go together. So sine, its reciprocal is cosecant, and so on. All right, so we could express cosecant as, it's the same as finding the derivative of 1 over sine x. This also could be written as sine to the negative 1 x, or sine of x all to the negative 1. Remember, this negative 1 in this position for trig functions, that's what it actually means. It actually means this. The reason why they write this is because, again, they don't want the exponent to be confused with being on the variable. They want to make sure that you know that it's the sine function that is to the negative 1, not the x to the negative 1. But, you know, if we're finding the derivative, this right here, right, this is a better way of looking at it, isn't it? All right. So now let's do that one. Let's do d over dx of sine of x to the negative 1. And, of course, we could use, we're going to use the power rule and chain rule. So, to find that derivative, we'll do the outside function, right, which is this right here, this blob here to the negative 1. And that's going to be negative 1 times sine of x to the power of, right, negative 2. And are we done? Yeah, we're, oh, wait, what? We're not done. Okay. So, right. Times what? The derivative of the inside function now, which is sine of x. The derivative of that is cos x. Okay. Simplify this. We have negative cos x over sine squared x. Make sense? So, could we leave it like this? Yeah, but if we're talking about finding a derivative of cosecant, okay, we don't want to mess around with, you know, with quotients, you know, negative exponents. No, we don't want to do that. So let me show you how we're going to get to a simpler version of this right here. We're going to simplify this a little bit. This is actually the same as negative. There's the negative. We've got two signs down here, right? So let's split them up. 1 over sine x times cos over sine x. Now you'd say, well, why would you do that, Mr. MathWell? That's a little bit of a silly way of splitting that up. Why would you do that? Well, here's why. Because negative 1 over sine x is negative what? Cosecant x. And cos over sine, well, let me see here. Let's see. Let's go back to here. Remember, tan is sine over cos. So if we had cos over sine, what would that be? Right. Cotan x. And so this is a way simpler way of expressing the derivative of cosecant x is this right here. Alright, so there's another one, and again, find these derivatives. You can simply rewrite them, and it's going to be easiest to rewrite them in terms of sine and cos, but now you could rewrite anything in terms of sine, cos, tan, or cosecant, right? And you could simply substitute and do your differentiation rules. So I'm just going to take a moment here. I'm going to display the chart of the derivatives of the trig functions that you're going to need to be concerned with here in this course, and we'll go from there. All right, so here's a little chart here. It's very similar to yours in your textbook. Thanks to beyondcalculus.com, where I got this little chart from. Here we have derivative of sine is cos. Derivative of cos, negative sine. Derivative of tan is secant squared x. Now, again, we like to put the squared right there, but it means the same thing. The derivative of, here's the cosecant, right? Negative cosecant, cotan. The derivative of secant is secant x tan x. The derivative of cotan x is negative cosecant squared x, or negative cosecant x squared. And I'll just maybe put that as well. So secant squared x, and this equals negative cosecant squared x. see, when you put the 2 there, you don't have to mess around with all these brackets either. See that? So it just makes a lot more sense. All right, so just take a moment to copy that down, just absorb that a little bit, and we'll do a couple examples here, and we'll set you up in your assignment. All right, so here's an example that we'll do. Here's a function right here, and of course we want to find dy dx. Okay. So derivative. Now you look at this and you got to figure out, okay, what is what? Where the 2 goes where? This 3 is. What does that mean? You know, all this. You might want to just write this. Okay, this is where you might want to get these brackets going. All right, and go like this. You might want to write this as this cubed is over this whole cosecant thing, because it's going to be a little bit easier maybe for us to see that this is the outside layer, right? The outer function here, if you will. So we need to differentiate there first. So let's do the power rule, bring that down, right? So y prime, or dy dx, is 3 times 2, 6, cosecant of 3x squared. Everything stays the same in here. 3 minus 1 is 2. Okay? Derivative of the outside function. That look good to you? Okay? Now we need to take the derivative of the next layer inside here. The derivative of cosecant. So what is the derivative of cosecant? Oh, there, I see it right there. Negative cosecant cotan. That's the one we just derived, right? So that is negative cosecant of what? Oh yeah, of the same thing. 3x squared. Negative cosecant cotan times cotan of what? Don't change a thing. Leave it all in there. Okay. This is the next round of differentiation right here. You guys see that? First, outside layer, that's the derivative of the outside layer. This is now the derivative of the second layer, right here. Now we need to go deep inside to multiply again by the derivative of the third layer in there, and that one's going to be easy, right? So that one's going to be times 6x. So here is the 1, 2, third layer right there. So that's really your first step. That's differentiation right there. Okay. To simplify, we go another step 2 here to simplify. But that is your basic differentiation of that function. We did the chain rule, right, along with the power rule and all that sort of stuff. But we used the derivative of cosecant there, right here. Okay. So if we want to further simplify that, I guess what we could do is take a look at this 6 here. You got a negative here. You got another 6 here. So what is that? Negative 36. Okay. We've got cosecant 3x all squared, and we've got a cosecant 3x to the power of 1 here. Right? So I guess we might want to just combine those. If we've got cosecant 3x squared and cosecant 3x squared to the power of 1, we can just go cosecant 3x squared to the power of 3. Right? Where would we put that 3? Right here. Cosecant cubed. Okay. 2, and then a 1 that would be there. Right? So just add exponents, same base, add exponents. And then we've got this lonely cotan 3x squared, so we'll just write that cotan of 3x squared. And there is your answer, dy dx, right there. Yes. Okay, here's our final example that we'll do here for 7.3 other derivatives of trigonometric functions. And this one here, okay, we can't really solve for y, and we're going to do dy dx. Okay, so the derivative of y with respect to x, we're looking for y prime. It might be easier for you to see that, hey, y is pretty tangled up in here with tan. No pun intended, tangled up. Yeah, I know, that's funny. So we can't get y all by itself because we can't divide tan off, right? You can't divide both sides by tan. That is just an absolutely ridiculous notion. So you can't do that. Okay, everybody knows you can't do it. Even the kids on the playground in grade 2. No, you can't do that. If you were to, seriously, if you were to ask them, say, can I divide tan out of tan of y, they would say, I don't know. So no would be in the answer. Okay. But I digress. I apologize. So we're going to do implicit differentiation. No problem. Is there a problem here? Nope, no problem here, sir. What we have to do, though, is find out what the derivative of tan is. Cosecant squared x. No biggie. Okay. So the derivative of this side is the derivative of tan, which is secant. Oh, what does it say? Is that right? Yeah, secant squared x. So this is secant squared, well, the variable is y. Okay. So the derivative of this is this right here. But we have y in there, and you know what? Y is not our preferred variable, so right, multiply by y prime. Chain rule, right? Outside function, inside function. The inside function is not x, so it's not what we're multiplying by 1. We're multiplying by the derivative of what this is, which is just y prime. Very good. Now, 2x on this side. Awesome. Okay, so what do? Well, what are you trying to solve for? Da-da-da. Where is it? Da-da-da. Okay, multiplied by this over here. How do you get rid of this? Da-da-da. Right? I'm not sure where the superhero music come from today. But y prime is going to be equal to 2x over secant squared y. Awesome. We done? It could be. Could be. Is there any way we could, I don't know, rewrite this without, a quotient? Any way we could yes, there is. Okay. Remember, this is the same as 2x times 1 over secant squared y. So what's 1 over secant? No co. That's 1 over cos. So 1 over secant squared is 1 over cos squared. So this actually, you could write this as 2x cos squared y. Da-da-da. Implicitly differentiated. Doesn't matter, we've got x in there and y in there. Who cares? We've got y prime all by itself, isolated. That's what we're looking for. If you're going to try and evaluate this, no big deal. You plug your x value of the point, so you got this graph, whatever. You plug the x value and the y value in. Boom, both of them. One there, you get your value. No big deal. Alright, so that's that. And that was the lesson on other derivatives of other trig functions. So to accompany, 7.2, derivatives of sine and cos. I hope you learned something, and you're ready for your assignment now. Alright, one other thing I should mention before I give you your assignment here is just some pre-calculus stuff here. And if you have to ever figure out, sine theta minus 1 equals 0, if you want to find out, if you want to solve for theta here, what's the angle that makes this statement true? Remember, you can't add 1 to both sides and then divide by sine to get theta. Remember, you can't do that, okay? So we're not going to do that. Instead, how do we do that? Well, remember, you use your unit circle. I have the unit circle over here. And feel free to get one out, whatever, if you got from last class or whatever. You should have a lot of this memorized already, though. If you have the first quadrant memorized and the quadrantal angles memorized, that's the ones on the axes here, you should be fine. So sine of theta equals 1. Well, what angles does sine of theta equal 1? Well, that's what you actually have to look at on the unit circle. Remember, this is the coordinates are cos, comma, sine. So where is the second number 1? Okay. Okay, in this spot right here. So what is the angle in question here? You have to look at the unit circle, and you say, okay, cosine. Where is sine equal to exactly 1? And it's right here at pi over 2. So this is how you solve trig equations. You have to remember that with the unit circle. Okay, you can't isolate for theta in any way. You have to do it that way. So that's just that thing right there. Also, if we're talking about a domain, right, of negative pi over 2 to pi over 2, if that's the interval, remember, here's 0 degrees. Negative pi over 2 is back here. Positive pi over 2 is over here. So we're talking about all of the angles from here to here. All these ones. That's the domain there. Negative pi over 2 all the way through to positive pi over 2. You see that? Okay? So where is, sine of theta? Where does sine of theta minus 1 equal 0 on this domain? Right here? Well, you look and you say, hey, sine of theta would equal 1 at pi over 2. So I'm looking at pi over 2, and you look at your domain, uh-oh, we're not including pi over 2. So guess what? There are no solutions here. You would say there are no solutions. Even though this is a solution, this is not in the domain. Okay, so you might have to just let that sink in for a little bit, but you might need, to remember that for some of your work going forward. All right, here's your assignment for 7.3. Take a second.